Okay. Right, onwards. So it's a pleasure to welcome Pierre Albin to our program this week. And he's very generously, I think, agreed to give a rather general talk introducing some of the analytical methods that are being used to study moduli spaces. I'm afraid I've forgotten I've got your title, global analysis. An introduction to
analysis on non-compact spaces.
Analysis on non-compact spaces. So, thank you.
Great. Well, thank you very much. Thank you for the invitation to speak. It's a pleasure to be here. So indeed, I've been asked to talk about general methods to study non-compact manifolds, do analysis. And so, of course, there are many approaches and many different contexts where these things apply. So I decided to just focus on the simplest setting, in some sense, of manifolds with cylindrical ends, and just talk about how things work out there. So the setting is we have a manifold with a cylindrical end. And our theme throughout is going to be to resolve the geometry to smooth objects, smooth non-degenerate objects on compact manifolds with corners, right? So that's also our criterion for knowing whether or not we've resolved it. If it's a smooth non-degenerate object on a compact manifold with corners, we're done. Otherwise, we're not. Right. So of course, the simplest instance is to start with our manifold with cylindrical end and compactify it. So let's say a cylindrical end looks like right cross R plus. So we're going to compactify it and introduce X bar, where we just add boundary at infinity. Right? So now this is a compact manifold with boundary, and we want to understand the geometry of the non-compact space on the manifold with boundary. So we're identifying the non-compact space with the interior of the manifold with boundary. So the sort of metrics, right, the fact that this had a cylindrical end is reflected in the metric that you study on the interior of X bar. And we're going to look at what are called B metrics. So this is a metric that has this form near the boundary. So let me tell you what X is. X is what's called a boundary defining function. Or DBF for short. So this is just a smooth function on the manifold with boundary. So it's smooth all the way to the boundary. It's non-negative, and it's equal to 0 precisely at the boundary, and it's only a first order 0 at the boundary. So that's why it's called boundary defining function. It's 0 set defines the boundary. Great, so you see that this metric is degenerating when x goes to 0. I should say what h is. H is just a symmetric 2 tensor. On the manifold with boundary, so smooth all the way up to the boundary, and this is called an exact B metric. I should say this philosophy, this approach is due to Richard Melrose, and it consists of putting B in front of everything, and, but interpreting that as like a change of category. Okay, so this is the metric. And as you see, it's clearly degenerating as x goes to 0. It's blowing up, right? And so in terms of our theme, that means we're not done with it. We want to resolve it until we have something smooth and non-degenerate. So if we're going to have this induce a non-degenerate metric, we're going to have to restrict the vector fields we look at. So let's call the B vector fields are going to be the vector fields that have finite pointwise, bounded pointwise length. with respect to this B metric. With bounded point twice length.
TX bar.
Sorry?
TX bar.
The X bar, thank you. So of course these have a very nice geometric description. These are precisely the vector fields that are tangent to the boundary. Okay, so these are the vector fields that have bounded pointwise length, and so this is where we expect to get a non-degenerate metric. So there's a very nice construction. You could either use the general Serre-Swan theorem, or in this case, you can use a rescaling construction due to Richard, where you show that there is a bundle, so there exists a vector bundle called the B tangent bundle, whose space of sections is the B vector fields. So what I really mean is that this comes with a map from this into the usual tangent bundle, such that if you use this map to push forward a section of the tangent bundle to the usual tangent bundle, the image, the B vector fields, right? So excellent. So let's see what's different about this bundle is that locally the B vector fields are spanned locally near the boundary, spanned by x dx and dy, right? So if you have something transverse to the boundary like dx, then you have to have an x in front of it because you need to be tangent to the boundary. Right? And this section, this vector field, as a section of the usual tangent bundle, vanishes at the boundary. Right? However, as a section of the B tangent bundle, it does not vanish at the boundary. Right? And that's easy to see because restriction to the boundary is the same as projection onto the sections mod out x times the sections. Right? So when you restrict to the boundary, you're really just modding out by things that vanish on the boundary. And x dx is not equal to x times the B vector field. Right? So as a section of the B tangent bundle, you should think of x dx as a single object. The x is not a coefficient. It's part of the basis element. Yes?
So the distinction between this and just looking at the tangent bundle and in the cylindrical metric is somehow extra regularity of the guys as you go to infinity?
Well, it's a different compactification or extension to the compactification, if you like. So this map J is a bundle isomorphism over the interior, right? But it degenerates when you get to the boundary. It has current.
No, but I think that what you're saying is right. That if you just think of the manifold of infinite cylindrical end, then it just gives you an extension to infinity. You know, you've added this compact stratum at infinity, and it just tells you how to extend that bundle smoothly to infinity.
So that, but in terms of the sections, I mean, the smoothness here
Is a regularity condition
is
of the
just,
sections.
and the regularity condition is just the
Smooth in e to the minus t.
Okay, okay.
Yeah, that's right. So if you were to rewrite this metric with using log x as t, then that's exactly what's going on. Okay, excellent. So this bundle, so even though it looks like from here that the restriction to the boundary would just be vector fields tangent to the boundary, in fact, this does not lose rank when you get to the boundary. Okay, so, and indeed, this does accomplish our initial goal. The B metric does induce a non-degenerate metric on the B tangent bundle. Precisely because we just looked at the vector fields with boundary pointwise length. Okay, so as I mentioned earlier, Richard's philosophy is that you should think of this as a change of category. So instead of having a manifold, a closed manifold with the usual vector fields, now we have this manifold with boundary with the B vector fields, and you should just move everything over with this change of category. So any differential geometric construction you would do on a closed manifold, you should do here and put a B in front of it. So in particular, the B cotangent bundle is just a dual bundle, the B tangent bundle, and it's locally spanned by forms like dx on x and dy, right? And again, dx on x would be degenerate, would blow up at the boundary as a section of the usual cotangent bundle, but it does not blow up at the boundary as a section of the B cotangent bundle. Differential forms. So a B to denote smooth sections of exterior powers of the B cotangent bundle. Okay, and so what I want to talk about is B differential operators, then what it means to be B elliptic, what it takes to be Fredholm, and then I will specialize to D plus delta and talk about the L2 cohomology of a B metric. And then I'll talk about some of the index theory for B metrics and B differential operators. And on the off chance there's time left over, I'll talk about analytic torsion for B metrics. So in particular, let's go ahead and introduce D plus delta. So D, the usual exterior derivative, and it defines a differential operator on B differential forms, really just by extension from the interior. So in the interior, a B differential form is the same as a standard differential form. And the exterior derivative extends from the interior to the closure with B differential forms. In terms of these basis elements, you can write any B differential form near the boundary in this way, with alpha and beta independent of dx. And if you look at D plus delta, right, delta is, of course, the formal adjoint of D. Then as an operator on B differential forms with respect to the splitting, this looks like D plus delta on the boundary, then minus x dx minus D plus delta on the boundary.
That last statement about alpha and beta, do you really mean alpha and beta are independent of x?
Sorry, no, I mean, there's no dx.
Right.
Right, that's all x. Yeah, so the. This is very nice and symmetric and only involves B vector fields. If we had not used this splitting, but if we had done splitting with respect to the usual splitting, then what we would have would look like this. So it's, of course, not very different. But it's not nearly as symmetric, and it does not, it involves vector fields that are not tangent to the boundary. So this decomposition certainly gives us something more symmetric. And in other geometric situations, it's more remarkable. The different, how much more symmetric it is when you do the decomposition with the appropriate forms. Okay, and so this fact that it only involves B vector fields is something we like. And so we'll say that a differential operator is a B differential operator, right? If locally you can write it using only B vector fields, right? So technically it's an element of the developing algebra of B vector fields. And all that really says is that locally you have a sum of an index and a multi-index of a polynomial in these space values. Okay, so to each such operator, let's call this.
You're somehow confusing x with x bar. I mean, everywhere you write x, it should be x bar. I mean, the original.
Yes, that's
In the sense that
that's
those
mostly on
coefficients are smooth
purpose.
up to the boundary.
That's right. So these
Yeah.
are smooth all the way up to the boundary. Yeah, but I would still write x here and just
Whenever there's a B, you assume it's an X bar.
there you go. Yeah. So thanks. Yeah, I suppose I really should.
Well, I just, there's a little potential confusion there.
Okay. But indeed, as you say, these coefficients should be smooth all the way up to the boundary, and there's no problem allowing vector bundles all the way up to the boundary. These should just then be homomorphisms locally between the vector bundles.
Again, smooth means differentiable as many times in terms of x dx.
This I mean smooth in the usual way. Differentiate with respect to the
It's a
x.
scalar.
Well, I'm just wondering which vector. Okay.
Right. Now, this
Smooth means smooth.
yeah, smooth. Yes, smooth being the usual smooth. No b's.
But so in particular, what this says, the right-hand side thing is that this D would not, or D plus there would not be a B differential operator acting on sections of the standard
That's right.
standard form.
That's right. Exactly. So, yeah, working on B differential forms, you do get a B operator, but not working on standard differential forms. Okay, and so to each B differential operator, we're going to associate two models, right? So on a closed manifold, you have just one model, the principal symbol. Here we're going to have two. So two models. One is going to be the symbol, but of course with a B. Right, so the B symbol is, well, this is a polynomial in the B vector fields. So we're just going to write this as a polynomial in dual variables. And we're going to keep only the highest order part. So this at a point P would be these coefficients at the point P, and then replace the vector fields with variables on the B cotangent level. So this is a smooth section of the function defined on the B cotangent bundle of x. Let's go far. I guess if there are no bundles, that's it. If you have bundles, then of course it's valued in homomorphisms. Pull back to the cotangent bundle. And so you can think of this just like in the case of closed manifold. This is like freezing the coefficients of the operator at a point. Right? So, and indeed, you can equivalently think of this on the B tangent bundle as a constant coefficient differential operator. And the second model is called the indicial operator, or the normal operator. And this is a B differential operator on the exact cylinder. And so basically you just freeze coefficients at the boundary and think of it as acting on the normal bundle to the boundary. So you have, in terms of this local expression, 1 less than or equal to L, frequency coefficients at the boundary, and then notationally we replace x with s, just to indicate that now it's acting on the entire real line and not just part of the manifold. So there are really good heuristic reasons for using this operator as an indication of how the operator acts near the boundary. As I'll mention in a moment, there's actually very good formal reasons for this being the model at the boundaries, not just heuristics. And it will show up very naturally in the constructions without having to introduce it artificially. Okay, so these are the two models. And we're going to say that a B differential operator is elliptic if its symbol is invertible. Right, off the zero section pointwise. So at every point, if we had homomorphisms, then we just want this value to be isomorphisms. So, and of course, that's often called E-elliptic. Okay, so next I want to discuss what you get from having an elliptic operator, a B-elliptic operator. And one big difference with elliptic operators on closed manifolds. So, first of all, elliptic operators, if you're B-elliptic, then in particular in the interior, you're just elliptic, right? And so you do have elliptic regularity on any compact subset away from the boundary. Now, if you think of elliptic regularity in terms of inequalities, then the constant will depend on where you are on the manifold. And because the usual symbol is degenerating as you go to the boundary, because you have x dx instead of dx, the constant is going to be degenerating as you go to the boundary as well. Right? So another way of saying this is, although the operator is elliptic on the interior of the manifold with boundary, it's not uniformly elliptic. And so you don't have a single inequality that holds on the entire manifold with respect to the usual subgroup spaces. So of course, the solution is to introduce B subgroup spaces. Right? So let's stick for the moment to K, a non-negative integer, right? And this means exactly what you think. You have elements L2 such that you hit them with K vector fields and you're still in L2, as long as the vector fields are B vector fields. So this is what you were referring to earlier. Now we're measuring regularity with respect to B vector fields instead of standard vector fields. Right? And so these are not necessarily, if you have this sort of regularity, it doesn't give you the usual regularity at the boundary. It's going to give you something else, which I'll get to in a moment.
But then is it the usual regularity on the cylinder like the original cylinder?
So in the interior, it's the usual thing. In the interior, you have the usual sublet spaces. Right? It's only, we're going to have, if you like, uniform sublet bounds because we're measuring regularity with respect to these vector fields. Right? Whereas in the interior, you don't have uniform sublet bounds.
But I think with saying you really just took the cylinder, think of it as like a local coordinate chart, saying the cross section. Think of it as a cylinder in like a strip in Euclidean space. Then it would be the usual sublab space, in fact. Up to infinity. I mean, there's in the uniform statement. I mean, this e to the minus t version.
Okay.
So it is the same.
I mean, the other way, the other way to say it is that the D sublet states are the ones associated with the cylindrical metric.
Right.
That's
Right.
right.
Yes.
That's
Right.
right.
Exactly.
So it is. But you don't have the end in that. You don't. I mean, So there's no boundary to talk about boundary regularity of in that picture, because t is also going on to infinity. Does that answer your question?
Okay. Did you have a question?
This is weaker condition than being smooth up to the boundary, because the vector fields
Right.
That's right.
have
So-
a vanishing.
Right, so something smooth in this sense will not have a Taylor extension.
Right.
necessarily.
At the same time, would this, if for some odd reason you were interested to use a different power of x in the metric, would this all work with a different power? Or is this specific to it being x to the first?
So the answer is yes, mostly. So it depends on exactly what power you pick and how things work out. But for example, if you were to just take x squared, so that the metric had an x to the fourth, then it works exactly the same. Right? But if you were to take x to the 1/2, then things are different.
But you're not introducing anyway, so like if I'm seeing in the cylindrical metric, or the, I can define weight symbolic spaces,
Yes.
and then do my analysis there. But this corresponds to the unweighted.
This is unweighted, that's right. We'll introduce weights.
So yeah, I mean, if you introduce any power of x, because, you know, you just have the b situation, so if you replace x by x to the a for any a, positive a, then it just becomes a multiple of the same thing. So in fact, you can take any power, any positive power of x.
Right, absolutely, but these are the unweighted. That's the question. These are
No, and what,
Also,
what
I
did
meant
cross
for-
question?
Oh,
I even meant for the things you're about to do also. So I think.
Right, no, but for this, yeah.
no, we're curious, yeah. Okay, so these are web spaces, and if you have an elliptic differential operator, you get a continuous operator from K to K minus L, so it's continuous. And if you have elliptic, then the domain of A as an unbounded operator on L2 is precisely HBL of x. Right, so that works exactly as on a closed manifold, right? The domain doesn't depend on the operator, just the order, as long as you're elliptic, and you have continuous maps. So that part all works exactly the same. What's different is that the being elliptic is not enough to be Fredholm. So let's look at, for example, the null space. All right, so if you have the kernel of A, then this is going to be inside the intersection over K of spaces. So this is HB infinity, right? But like we've been talking about, these elements are not necessarily smooth at the boundary. They don't have a usual Taylor expansion at the boundary, but they do have something at the boundary. So, okay, so let's think about elements of the kernel. So let's define the B spectrum of an operator. These are going to be complex numbers such that there exists the smooth in Y with A of x to phi equal to theta x plus 1, right, with an appropriate cutoff function. So we're interested in elements of the kernel. So in particular, if they have some sort of leading order, that leading order should get better once you hit it with A, right? Notice that A, being a polynomial in x dx and dy, generically would preserve the order of vanishing at the boundary. It would take something of order x to the zeta to x to the zeta, right? So this is something extra, right? And you can phrase this in terms of the initial operator. Since we're working right next to the boundary, it doesn't matter. And in terms of the initial operator, then this is looking for something in its null space. There's a refined version where you take into account logs in the order. So you can define this as pairs, complex number, non-negative integer, where you do the same thing, but this is a smooth function in y. So this is the initial operator. Vanishes on x to the zeta log x to the b. And so again, our motivation here is that we want to study elements in the kernel. If they have some sort of leading order, then that leading order has to be in these sets, because we have to have extra vanishing at the boundary. So here's a very nice fact. If you have a lithic, you have an element of some weighted space, and when you hit it with A, you end up in a better weighted space. Then you have a partial asymptotic expansion of the boundary. Right, well, let's add a cutoff function. So you have a sum of sum y with powers like we have over there, plus some remainder term, where in the sum we have elements of this extended B spectrum. Right? These are also called initial groups. And we want these to stay inside. Which ones we allow are determined by what weights we have. So we want A less than the real part of Sj, and real part of Sj plus L should be less than A prime. L runs along non-negative integers, and there. And then U tilde lives in the better weight space.
The powers of the logs might increase, though. I mean, it's not quite the spectrum of A, it's the spectrum of A extended union itself plus integers and all of those. I mean, I think the order of the logs can increase a little bit.
Okay, that might be. I think you can get away with this, but sure. In any case, let's say log power is pretty good. Okay, so in particular, if you're in the null space, then here you can put A prime arbitrarily large, and so you end up with an asymptotic expansion. So this is the behavior you have at the boundary. Instead of having just a Taylor expansion in X, you have these crazy coefficients and possibly logs. Okay, so why is this true? Well, there's a wonderful tool for studying asymptotic expansions like this, which is the Mellon transform. Right, so the Mellon transform is it's just a Fourier transform in exponential coordinates. Right, so you have right, so if you like, the Fourier transform comes from the additive structure on the real line. The Mellon transform comes from the multiplicative structure on the non-negative part. And this is an isometry between L2 with respect to a B density, so dx on x, and an L2 of a equal to 0 with respect to pi, where variable zeta is equal to chi plus I eta. Okay, so
What's the regularity?
these coefficients are smooth in y, and the leading term for a given initial group is in the kernel of the initial operator. So maybe you're thinking of the edge setting where you lose regularity in z, but there's no z. Right, okay, so the Mellin transform, and so what ends up happening is if you're in L2b, then you're in L2 at eta equal to 0 after you've taken Mellin transform. But if you're in L2, you're also in x to the minus epsilon L2 for all positive epsilon. And so, in fact, you end up being holomorphic on a half plane. So if you look at something like x to the zeta log x to the p, and then multiply this by some sort of cutoff, this has Mellin transform that is holomorphic in eta less than real part of theta. It extends meromorphically to the entire complex plane, and it has a pole precisely at I times theta, so it extends meromorphically to the complex plane with a unique pole at I theta of order p plus 1. Right? So if you take this guy and take its Mellin transform, then the meromorphic structure of the Mellin transform tells you exactly what exponents you had here. Right? And because this is an isometry, you can just move the contour and come back. Right? So this characterizes having this sort of expansion. Right? So what this means is if you want to establish this expansion for u, what you need to do is look at the Mellin transform of u, cut off near the boundary, and find out where its poles are after you normalize the continuum. So if you write A near the boundary as I of A plus an error, okay, so these are the leading terms with respect to x dx and dy, and these are terms where the coefficients have extra vanishing, then the Mellin transform of u and theta is is given in terms of the Mellin transform of these things in this way. So and there's an I. So the initial family of an operator is what you get from the initial operator by conjugating by the Mellin transform. And so all it is, well, actually, I'm going to define it where you just put a theta instead of an SDS, right? But you leave the dy, right? So it's a homomorphic family of differential operators on y. And if you conjugate the initial operator by the Mellin transform, you get the initial family, but with an I theta, because I theta up here. Right? Now, by analytic Fredholm theory, the initial family, if it's invertible anywhere, it's the inverse is a meromorphic family of operators. So this is meromorphic, and it's going to have its poles precisely where the initial family is not invertible, which from here is going to be in the B spectrum. So great. So then in this setting, U started out in x to the A, so the left-hand side is homomorphic for eta less than A. A times U is an x to the A prime L2, so this is holomorphic for eta less than A prime. This is holomorphic because E had this extra factor of x. This holomorphic in up to A plus 1, right? And this is meromorphic with poles at the B spectrum, right? So between A and A plus 1 or A prime, whichever comes first, this expression gives us this partial expansion. And then you just iterate. Right? And that's where the else come from. Because you could have a pole coming from here, from the previous step in the extension of the meromorphic.
Yeah, so that L is not the order of the operator.
Oh, thank you. No, this is going through the integers. K. Is there K's anywhere? I think I'm safe with K.
Yeah, you are.
Yeah. So K.
And that.
Yes. So K is running through non-negative integers until you get to A prime.
But the order of the log can increase if you have two initial roots that differ from each other by a positive integer that's in that strip. And then,
Yeah, yeah, I think you're right. So you're saying when this hits that,
Yeah.
you could decrease the size of the log. Okay. Okay, fair. Okay, so this is the structure of elements in the kernel. Well, in fact, this is just some gain in decay. How that reflects on you. So if you like, this is like elliptic regularity at the boundary, right, in terms of decay as opposed to regularity. Okay, so that's what I want to say for elliptic operators. Next, let's talk about what you need for Fredholm. Right? So elliptic was just the invertibility of the symbol. For Fredholm, what we're going to want a Fredholm on a weighted L2 space, so as an unbounded operator, right? So with its domain shouldn't be solo space. This is going to correspond to having both the symbol, this invertible pointwise, and the initial operator invertible on the corresponding weighted L2 space. Right? So again, this makes a lot of sense heuristically, and I'll tell you why it's exact in a moment. But heuristically, we even have a theorem by Engel that says that, I think he was working in spaces bounded geometry, but you have a non-compact space and an elliptic operator. For it to be essentially injective, what you need is that it is bounded below at infinity, right? So that is, there is a compact set, and any section supported outside that compact set, U, when you hit it with the operator, the norm of AU is bounded below by a constant times the norm of U, right? So that's saying that your operator is invertible near infinity, right? And so that corresponds, heuristically anyway, to I of A being invertible on this model space, and we'll see that it corresponds exactly to I of A being invertible on that space. Okay, so to lead up to that, let's look at what an inverse of such a thing would look like. Right? So let's take a very simple case. Let's say that operator looks like x dx minus some operator on y. Right? This is our initial operator. And you want to invert that. Right? So let's just ask if you have x dx minus this operator acting on a function f and you got a function h, right? What is f in terms of h? Right? And of course, x dx and dy commute, so you may as well pass to an eigenspace and replace that with a constant, right? And then you're in really good shape because you can rewrite this as x to the mu, x dx, x to the minus mu, f. Right? And so then you can just write down the solution unit f of x is equal to we move from 0 to x of x over x prime to the mu h of x prime dx prime over x prime. And then if you want to integrate over the entire line, you just throw in head of that function. Right? Right, so that's the inverse on the nose for this one-dimensional guy, and by the spectral decomposition, we can have the dy there. Right? So we want to understand the integral kernel, right? And again, our theme is that when things are degenerate, we should change the compactification or something to make them non-degenerate, right? So we do have a singularity here on the boundary, on the diagonal, but I want to focus on the first term, this x over x prime, right? Because if you're looking at r plus squared, right, and you're looking at x over x prime, then that's going to have, well, it's not going to have a limit at the corner, because if you approach along any of these lines, you get a different answer, right? So what we do is we introduce polar coordinates around the origin, and then we take them seriously, right? And so by taking them seriously, you know, when you're teaching calculus and you introduce polar coordinates, tell your students that at r equal to 0, at any angle, you get the origin, which you do, right? But what we're going to do instead is we're going to keep track of that angle, right? So we're just going to replace this, this point, the origin, with all of the angles at r equal to 0 that correspond to it. And here, x over x prime has a limit as you approach. Okay, so this is called the double space, and this, of course, called the B double space. This is the situation when you're working with R+, but in the general case of manifold with boundary, we define x squared b to be x squared, and then you do a radial blowup of the corner, right? This is the notation for radial blowup. And radial blowup means take this submanifold and replace it by its inward pointing spherical normal level. Right? So just introduce polar coordinates around this point and then take them seriously. This is a manifold with corners, by which I'm going to mean a space that's locally modeled on R plus to the n, right? Meaning that any point has a neighborhood diffeomorphic to the neighborhood of some point, not necessarily the origin in here. And it's good to demand that you have embedded boundary hypersurfaces. Because then you have boundary defining functions, and those are really useful. Great, so this is the B double space, and I want to stare at this a little bit. So one thing to note is that the diagonal, right, which remember these guys, these explicit kernels had singularities along the diagonal, right? So notice diagonal is much better behaved over here than it was over here, right? Because it hits the boundary now at the interior of this boundary hypersurface instead of hitting the corner. You can look at what the normal bundle is, and the normal bundle in here, really the lifted diagonal, is canonically isomorphic to the B tangent bundle, right? So that's really useful, and it points to this being the correct space to work on, right? So for example, if you look at operators whose Schwartz kernel is supported on the diagonal, this tells you that what you get is a B differential operator. And And it also allows us to define the pseudo-differential operators there as polyhomogeneous conormal distributions on the B-vector space. Okay, so if you're familiar with pseudo-differential operators, then this is what it usually means, right? If you're not familiar with pseudo-differential operators, don't worry about it. What this means is we have distributions that are singular only on the diagonal, and it's a very nice singularity there, in that the transverse Fourier transform gives you a symbol. Right? The symbol that you get lives on the conormal bundle, and so it's going to be the B cotangent bundle, which is exactly where we wanted to have symbols. It's where we have them for B differential operators. Okay, and then the polyhomogeneity. By polyhomogeneous, I mean that you have an expansion that looks like this. So in terms of some powers of x and powers of log x. And you see that we expect something like that from this explicit example because we have this x over x prime to the mu. And so it's going to have some sort of expansion at this face and at this face. Okay, now, so now let's say that you're in this situation. You have the symbol of A invertible and the initial operator of A is invertible, right? So now let's construct the parametrics. For A, so what you do to construct the parametrics, you have the B double space and you have, so this is an interesting face and then you have a singularity on the diagonal. So first, let's think about what would happen if you had a B differential operator. So I said the integral kernel is completely supported on the diagonal. If you restrict to the front face, it's called, the new boundary face, then you get the integral kernel of the initial family once you take into account that you have the R plus values, right, of the line and the initial operator. And so the integral kernel that you get here is precisely the initial family, right? So that means that here what we should put is the inverse of the initial family acting on this model space. Right? And here we're going to have to put a symbol, so of course we should put the inverse of the symbol of A. And of course these are compatible where they meet, so you can find distributions like this. And any such, so if any such B has identity minus AB and identity minus BA compact operators on XBA L2B. So you get a Fredholm parametrics from any distribution with these model operators.
So it might just be helpful to mention that, so S can be interpreted as a natural coordinate along that.
Thanks, yeah,
line,
exactly. Thank you.
with respect
yeah.
to which it's exactly x over x prime.
That's right. Thank you. Yes. Yes, okay. So this is how you get a parametrics, and so that's why you need those two conditions. And the fact that the model that you get at this space is what I was alluding to earlier, that the initial operator starts out as a like heuristic of what you should be looking at, but in fact it's very precise. It's the operator that you get at this space, and so you really have no choice as to what model you have to invert. Okay, so this is how you get a parametrics, and it's useful to rewrite this condition, the invertibility, the initial operator in terms of the initial family. So what we need, so if A is elliptic, then A is Fredholm on L2A, L2B if the real part of A is not, well, I guess A is real. Say, if A is not in the real part of zeta for some zeta in the initial roots of the spectrum. So you have this discrete set of weights, and for any other weight, you end up with a Fredholm operator. It follows from that even when you don't have a Fredholm operator, you do have finite null space. Okay? So what's going wrong is that you don't have close range. You have continuous spectrum going on. Okay, so with all of that background, for general the elliptic operators, now let's focus on L2 cohomology. Okay, so we have a manifold with boundary. So one cohomology that we're all familiar with, if you just take differential forms on X with smooth all the way up to the boundary and there's nothing involving the metric, then this just gives you the absolute cohomology of X. And if you were to use differential forms with compact support, then you get the relative cohomology. So now we want to bring in the metric. So let's define, put a B and a L2. These are going to be differential forms in L2 of X bar. B differential forms such that D is again in L2. So this forms a complex rather automatically, and so you could look at its cohomology, and in fact the cohomology of this complex, which is what you would usually call L2 cohomology, which is L2 cohomology of the maximal extension, this is usually infinite dimensional. Well, in fact, if I haven't put any twistings, it's always infinite dimensional. Right, and the reason is, well, let me tell you what is finite dimensional, and that'll tell us the reason. So I'm going to denote H2 bar of K X to be the kernel of D on this complex. And I'm going to run it out by the image of the same complex when we get the closure. Right? And so, of course, what goes wrong over here is that the image is not closed, and so the quotient is automatically infinite dimensional. But if you mod out by the image, then you can use a Kadira decomposition to see that this is equal to kernel of D intersects kernel of delta, which I'll denote with a curly H. So from what we've seen before, and the fact that D plus delta is elliptic, tells us that this is finite dimensional, and we want to identify it. So also what we saw before with the asymptotic expansion for elements in the kernel, we know that if you have a differential form in here, then in fact this differential form is in a weighted L2 space. It has some vanishing for small enough epsilon. Right? So, and this is just from the asymptotic expansion. There's going to be some room before you get to the first initial root, right? So you have that much extra vanishing. So this recommends that we look at the complex of weighted L2 differential forms, and that's easy to compute. So the cohomology of weighted L2 differential forms is a relative cohomology for any positive delta. And this is quite easy to see. The point is that if you have a form near the boundary like this, and you know that it's closed, then closed tells you that dy alpha is equal to 0, and x dx alpha is equal to dy beta, right? And you can integrate this equation to find that alpha is equal to the integral from 0 to x of dy beta dx on x, right? So the only problem is, does the integral converge? And if you have a positive weight, then it does. Because any weight with a dx on x converges positively. So then what you do is you look at the map, take u to u minus d of some cutoff function integral of beta dx on x, which you can rewrite as 1 minus chi times u minus chi prime dx wedge integral. And from this expression, you see that you ended up with a form with compact support. So this sends weighted B differential forms to forms with compact support. It sends closed forms to closed forms, exact forms to exact forms, so it induces mapping cohomology. And the obvious inclusion of compactly supported forms into here is an inverse. So this is an isomorphism, and we're done. Okay, so great. So if you have for a positive weight, then you get that if you have a negative weight, then you get the absolute cohomology, right? And this is just because the usual intersection pairing of differential forms puts this cohomology and this cohomology in duality, and it also puts this complex and this complex in duality. So this equality has to follow. So the interesting case of delta equal to 0 is a bit more complicated. Okay, so the answer is that the reduced L2 cohomology, this is just a Hodge cohomology, is equal to the image of relative and absolute. So the inclusion of the boundary into the manifold induces a long exact sequence, and you're looking at the image of relative in absolute with respect to that. Okay, so proof, so I'll follow the exposition in Hausel, Hansaker, and Zell. There's an obvious map from here to the image, because as we noticed here, if you have something in the Hodge cohomology, then it actually has some degree of vanishing, right? If you have some degree of vanishing, then because of this this lemma, you have a class in relative cohomology, and then you just map that class to absolute cohomology, and that gives you something in this image. So we want to see that this map is an isomorphism, right? So let's check injective. So how could injective fail? Well, I give you a class in the Hodge cohomology, so an element of the null space of P and delta, and you map it over here, and it turns out to be exact with respect to the absolute cohomology, right? So injective, let's assume U is in here, and U is equal to d theta with theta in x to the minus delta differential forms for small enough delta. Right? So because U is in the Hodge cohomology, I can take U and write it as alpha plus 0.x wedge beta, and alpha and beta will be of order x to the, let's call it lambda bar. So this would be the smallest eigenvalue of the Hodge-Laplacian on y over all degrees, the smallest positive eigenvalue. So if I pick delta smaller than this lambda underline, then I can integrate by parts without any boundary term, and use the fact that U is harmonic to see that that vanishes. And then for surjective, okay, so you give me somebody here, I have to find somebody here that maps to it, right? Okay, so you give me somebody here, let's say you give me a form with compact support. So I can represent it with a form with compact support. Okay, so now to find it in here, what we're going to do is use the fact that D equals delta is Fredholm on x to the minus epsilon L2 differential forms for any small enough epsilon, right? Because it's only a discrete set of weights where you're not Fredholm, right? So if I go down to small epsilon, I will be Fredholm. So what I care about from there is that it has close range, and so I can find generalized inverses. Right? So there's one canonical one using the Hilbert space structure, but really, given any space transverse to the image, complementary to the image, I have a generalized inverse, a skewed generalized inverse corresponding to that space. Right? So the thing to note is that the annihilator of the image of D with respect to the pairing between x to the minus epsilon and x to the plus epsilon, given by the L2 inner product, is precisely the Hodge cohomology. It's for small enough epsilon. And the reason is that if you have something in the kernel for small enough epsilon, then because of this, you're getting precisely the elements in the kernel at L2. So, there exists a bounded operator on x to the minus epsilon L to the d of differential forms, such that the identity on this space is equal to dg plus p with image of p inside Hodge cohomology. Okay, so I take a skew generalized inverse. So applying that to u, I can write u as equal to dv plus u prime, where u prime is where I want to be, and v is in x to the minus epsilon L2. Right? So we're almost there, because we want to show that we can represent the class of u with u prime, right? So I'd be happy if this were just the exterior derivative of v, right? So all we need is the delta v vanishes, right? And then we'd be fine. Okay, so let's stare at v a little bit. So we know that dv is equal to u minus u prime, and this is in x to the epsilon L2, right? This in fact has compact support, and this guy is in x to the epsilon L2 because it's in the Hodge cohomology, right? So we can use the partial asymptotic expansion to say that dv is a v is equal to, let's say, alpha of v plus dx on x, wedge beta of v, where these are of 1, plus b tilde, and b tilde would be x to the epsilon L2. Right? Okay, so now let's compute delta v paired with delta v. I can write this from here as u minus u prime minus d v delta v. So these guys have enough vanishing that I can integrate by parts, and they're in the kernel of d. So if I integrate by parts, they vanish. Right? This guy does not, because I have these terms that are of 1. Right? But I can use Stokes' theorem to compute exactly what the boundary term is from the integration by parts. Right? Of course, when the d hits this, you get 0, so I just get the boundary term. And the boundary term is with obvious abusive notation, alpha of dv plus versus minus 1, and beta of d. And this is pairing in y. But alpha of dv, that's just dy of alpha of v. Okay, now in this partial asymptotic expansion, the leading terms have to be in the kernel of the initial operator. The initial operator for d plus delta tells us that in fact both of these are harmonic on y. So in particular, it's closed. And so this is 0, and we're done. So that's the computation of the L2 cohomology. And as you see, it used all of the theory we had built up for elliptic operators, partial asymptotic expansion. Okay, so very briefly, I want to tell you about the index theorem for B Dirac type operators. Now, by Dirac type, I mean you should think Dirac type. I'm just going to work with D, so I don't have to introduce anything else. But we're going to use some notation that's standard in index theory. We're going to take our bundle E, which is the differential forms, and we're going to assume that it splits as a direct sum of two bundles. Right? We're going to assume that our manifold is even dimensional. We're going to take gamma to be the grading operator here, so it's +1 here and it's -1 there. We're going to assume that the operator we're looking at is odd with respect to this splitting. So for example, you can think of d plus delta, where either you're grading with respect to the parity of the differential form degree, or you could, if you have an orientation, you could use the Hodge star to get the self-dual and anti-self-dual forms. Okay, great. So let's say you are in a closed manifold. What do we do? So, following McKean-Singer, you would look at the supertrace of the heat kernel. The supertrace just means the trace when you've composed with the grading. Now, the supertrace, as t goes to infinity, gives you the index, where the index means the current dimension of the kernel of this guy minus dimension of the kernel of that guy. As t goes to 0, you would get something local, which McKean-Singer conjectured, and it was later shown, is exactly the integrand of the Singer index theorem. So it's a characteristic number. And then the beautiful thing is that this is independent of time. So in fact, these limits have to be equal, and that is the Singer index theorem. So what do you do in the B case? So now let's say there's a B case. So you want to follow the same steps, right? So start with, what can you say about the heat kernel? So again, let's be guided by the one-dimensional case. So let's say you wanted to find the heat kernel in just R plus, working with this operator. Well, you would switch coordinates to T, right, to the cylindrical end. You would find
R.
the heat kernel. R?
T's already used.
Oh, thank you, yes. So R, so have the cylindrical end, and find the Euclidean heat kernel, write it down in one dimension, and then switch coordinates back to X. And so what you would get is 1 over square root of 4 pi t times the exponential of minus log of x over x prime squared over 4t. Okay, and so now we're going to stare at that with our general theme of anything that's degenerate should be made non-degenerate. Right? We should end up with things that are smooth or at least polyhomogeneous. So the first thing is that we have this x over x prime, but we've seen that just means that you should do the B blow. You should blow up the corner, and then that will be smooth all the way to that face. Then we also have this quotient where you have t here and this log of x over x prime on top. So when t is 0 and the top is 0, we have some ambiguity. Right? The top is going to be 0 precisely on the diagonal, so we should also blow up the diagonal at 0 time. So this tells us, well, we have the square root of t. So there we're just going to introduce tau as a global variable, square root of t. And then the heat space, which of course is going to be called the B heat space, is going to be take x squared cross r plus with tau, and then you do the B blow for all time, and then you blow up the diagonal at time equal to 0. So what this looks like is this manifold with corners, where you have time, x, and x prime. Okay, and then the construction of the heat kernel is very much like the construction of the parametrics, also in the sense that I'm not going to do it. But I'll tell you how you start is, well, here, your operator is going to induce the initial operator here. So what you should put on this face is just the heat kernel of the initial operator. And then at this phase, what you should put is the heat kernel of the symbol, where by that I mean this face can be identified with the B tangent bundle. The symbol of your operator induces a constant coefficient differential operator on the fibers. So you take the heat kernel and set time equal to 1. Right? You set time equal to 1 basically because of the homogeneity. You're using homogeneous coordinates here, and so time just gets put into the coordinates. Or you can work it out, you have some radial vector fields and some Fourier transform. But anyway, those are the model operators you should put at those faces, and then, as before, you can solve away errors until you get the actual heat kernel without having modified what you put at these faces. The heat kernel ends up vanishing to infinite order at all the other faces. Okay, so that's the heat kernel, that's fine. So now let's just start this proof, and we run into a problem right away because the heat kernel is not trace class. It's not finite. Right? If it were, it would be given by taking the Schwartz kernel of the heat kernel, restricting to diagonal, integrating with respect to x on x and y over your manifolds, right, by Litsky's theorem. And the problem is that this is not finite. It's not finite because the integral kernel is O of 1 here, and if you're O of 1, then the x on x is not integrable, right? So what you do is you consider, for any function, say you wanted to regularize this integral, then you consider this function where you have an x to the s times your function. So this converges as long as s is positive. If you think let s be complex, then it's a holomorphic function for the real part of s positive. It has a meromorphic continuation to the complex plane as long as f is smooth. And near 0, this looks like 1 over s times the integral over y of f restricted to y plus something we're going to call the renormalized integral of f, and then things that vanish. So this is just the integral on the boundary, but in more general context we would refer to it as the residue integral, whatever comes with 1 over s, and this is the renormalized integral. So you can take the renormalized integral of the heat kernel restricted diagonal and you call that the renormalized trace, and then we're in business. So the renormalized supertrace of the heat kernel, as time goes to infinity, if you have a Fredholm operator, this converges to the index. And as t goes to 0, this gives you the usual local term by the local index theorem. In particular, this integral does not need to be renormalized. And okay, but then we run into another problem that this is not independent of time. So what you do is you write that the index is equal to this integral, so the usual local term, plus the integral 0 to infinity of the derivative with respect to t of the renormalized supertrace. And a very nice computation that I don't have time to do identifies this with the eta invariant of the boundary, the induced Dirac type operator on the boundary. So you get the Atiyah-Patodi-Singer index theorem as the index theorem in the B category. Right? In like the strong sense that you actually get the proof of the index theorem as by just taking the proof of the index theorem and putting B's everywhere. And actually this works even if the operator is not Fredholm, but then you get a more complicated thing on the left-hand side. But I think that's a good place to stop. So I'll stop there. Thank you very much.
Are there any questions?
Maybe just a comment.
Yeah.
Historical comment. This big calculus is pseudo differential calculus. It's lots of things. It's very straightforward. Maybe you may have mentioned that this freedom properties, the existence of parametrics, that was not much long before.
Yes. Yeah. So
that was our works in the 60s and 70s. People knew how to do it.
right. So I glossed over the history completely. Yes. So I apologize for that, but there was just no time to include history as well as the exposition.
Anything else? Okay, let's thank Pierre again.